We're all time travelers. Right now, you're moving forward through time at exactly 1 second per second. But Einstein's special relativity revealed something extraordinary. The faster you move through space, the slower you move through time. This isn't science fiction. It's been proven with atomic clocks on jets and particles and accelerators. If you could board a spacecraft traveling at 99.9% the speed of light, something bizarre happens. While a few years pass for you on board, decades or even centuries tick by on Earth. When you return, everyone you knew would be older or gone. You've effectively traveled into their future. This is called time dilation, and it's the only form of time travel we know absolutely works. GPS satellites experience this effect constantly. They orbit high above Earth where gravity is weaker and they're moving fast. Their clocks tick slightly faster than ours on the surface. Engineers must correct for this using Einstein's equations, or your navigation would drift miles off course within hours. The catch? This only works one way. You can leap forward in time, but there's no mechanism to go back. Gravity doesn't just pull on matter, it pulls on time itself. Einstein's general relativity showed that the stronger the gravitational field, the slower time passes. Near a black hole, this effect becomes extreme. Imagine hovering just outside the event horizon of a supermassive black hole. From your perspective, everything feels normal. Your heartbeat, your breathing, your watch all tick at their usual rate. But if someone far away from the black hole watches you through a telescope, they see you moving in slow motion. Your clock crawls, like your gestures stretch into eternity. And from your vantage point, you watch the entire future history of the universe unfold in fast forwards. Stars are born and die. Galaxies collide. Civilizations rise and fall, all while seconds pass for you. If you then escaped the black hole's pull and returned to distant space, you'd find that millions or billions of years had passed. You've traveled to the future, but there's a darker side. Once you cross the event horizon, you're cut off completely. The universe you knew ceases to exist in any meaningful sense. You've been severed from your own timeline. Wormholes emerge naturally from Einstein's equations. They're theoretical tunnels connecting two distant points in spacetime. Picture the universe as a flat sheet of paper. You're on one edge, and your destination is on the opposite edge. Normally, you'd have to travel the long way across, but if you could fold the paper and punch through, you'd create a shortcut. That's a wormhole. Now here's where it gets strange. If one mouth of the wormhole were accelerated to near light speed and brought back, time dilation would cause that end to age more slowly than the stationary end. When you reconnect them, one mouth exists in the past relative to the other. Step through the future mouth, exit through the past mouth, and you've traveled backward in time. The problem? Keeping a wormhole open requires exotic matter with negative energy density. This material has never been observed and may not exist. Without it, the wormhole collapses the instant anything tries to pass through. Even if you solve that, there's another issue: causality. If wormholes allowed easy backward time travel, the universe would be flooded with time travelers from the future. We see none. That absence suggests nature has safeguards we don't yet understand. Cosmic strings are hypothetical defects left over from the Big Bang. Imagine the early universe cooling and crystallizing like ice forming on a pond. Sometimes cracks appear. Cosmic strings are those cracks. One-dimensional flaws thinner than an atom but unimaginably dense. A single centimeter of cosmic string could outweigh Mount Everest. Their intense gravity warps space-time around them. Physicist J. Richard Gott proposed that if two infinite cosmic strings pass close to each other at near light speed, they'd twist space-time so severely that closed time-like curves would form. These are paths through space-time that loop back on themselves. A spacecraft following the right trajectory around these strings could return to its starting point before it left. You'd arrive in your own past. The model is mathematically sound within general relativity, but the requirements are absurd. You'd need cosmic strings with the mass of half a galaxy, positioned and moving with perfect precision. Even if they existed, approaching them risks getting trapped in a black hole or severed from the rest of the universe forever. No cosmic strings have ever been detected. They remain purely theoretical, remnants of a primordial universe that may never have formed at all. Frank Tipler proposed one of the strangest time machines allowed by physics. Take a cylinder, make it infinitely long, and spin it at nearly the speed of light. The rotation is so intense it drags space-time around with it, twisting it into closed loops. A spacecraft spiraling around this cylinder in the right direction could travel backward in time. Spiral the other way, and you go forward. The math works. General relativity permits it. But the engineering is impossible. The cylinder must be truly infinite. Any finite version would collapse or fail to produce the necessary spacetime curvature. It would also need density and rotational velocity far beyond anything we can achieve. You'd need materials stronger than anything in nature and energy output rivaling entire stars. Even if you built it, there's a deeper problem. The Tipler cylinder may create causality violations. You could travel back and prevent your own departure. Physicists suspect the universe has hidden mechanisms that prevent such paradoxes. Stephen Hawking called it the Chronology Protection Conjecture. The laws of physics conspire to make time travel impossible at large scales. The Tipler cylinder may simply break down before it can function. It remains a beautiful mathematical curiosity with no path to reality. Here's the most famous problem with backward time travel. You go back in time and prevent your grandparents from meeting. Because of this interference, they never marry. So your parents are never born, and you are never born. So how did you go back in time to stop them? This is the grandfather paradox, and it reveals why backward time travel seems impossible. But recently, physicists have explored a disturbing solution. What if the universe enforces self-consistency? Not by preventing you from acting, but by warping events so paradoxes can't occur. You try to stop your grandparents from meeting, but every action you take somehow leads them together. You trip and knock your grandfather into your grandmother, your interference becomes the reason they meet. The timeline locks into place. Calculations show this could happen even at the quantum level. Particles traveling through time loops arrange themselves to avoid contradictions, but there's a cost. In some models, traveling through time loops could erase your memories. Events might reverse, including aging. You could grow younger as you loop backward. Irreversible events, even death, might temporarily unhappen inside the loop. The person who emerges from a time loop may not be the same person who entered. Your identity, your history, everything that makes you you could unravel. Quantum mechanics introduces a bizarre possibility: particles communicating backward in time. It starts with entanglement. Two particles become linked, so that measuring one instantly determines the state of the other no matter the distance. Einstein hated this. He called it spooky action at a distance, but experiments prove it happens. Here's the weird part. Some physicists now believe the connection isn't through space, it's through time. When you measure one entangled particle and change its state, it sends a message backward in time to when the particles were first entangled. The past updates and the other particle reflects the change in the present. This is retrocausality, and it avoids paradoxes through quantum uncertainty. Before you measure a particle, it exists in a cloud of probabilities. It hasn't collapsed into a definite state yet. If you go back and change it, you're only altering probabilities, not rewriting fixed events. The history was never written. Recent experiments by physicists like Nicole Younger-Halpern suggest this could be testable. Using quantum computers, they've simulated particles sending information to their past selves. It works 1 in 4 times, reliably. If this holds in real experiments, it means backward time travel exists at the quantum scale. You might never send a person into the past, but you could send a signal. Imagine asking the future a question and getting an answer immediately. Rotating black holes, described by the Kerr solution, have a region called the ergosphere. Here, spacetime is dragged around by the black hole's spin so violently that closed time-like curves may form. These are loops in spacetime where following a path forward in time brings you back to where you started. In principle, you could enter the ergosphere, follow one of these curves, and emerge in your own past. The mathematics allows it. But survival is another matter. The gravitational forces would shred any known material. You'd also need to avoid the singularity at the black hole's center, a point where space-time curvature becomes infinite and physics breaks down. Most physicists believe quantum effects would destroy these curves before they could be used. Particles would build up along the loop, creating a feedback effect that destabilizes the geometry. Stephen Hawking argued that nature forbids time travel by collapsing any structure that might allow it. Still, rotating black holes remain the most plausible natural location for closed time-like curves. If they exist anywhere in the universe, it's there. And that raises an unsettling question. Are there regions of space-time hidden near black holes where time loops backward on itself, inaccessible but real? Miguel Alcubierre proposed a way to travel faster than light without breaking relativity. Instead of moving through space, you create a bubble. Space in front of the bubble compresses, and space behind it expands. The bubble itself and the ship inside can move faster than light relative to distant observers, but locally, nothing violates the speed limit. Here's where time travel enters. Causality and faster than light travel are linked. If you can outrun light, you can, in certain configurations, arrive before you left. Some physicists suggest that two Alcubierre bubbles traveling at different speeds could interact and create closed time-like curves. The result, backward time travel. The problem is familiar: exotic matter. The drive requires negative energy to warp spacetime, and no one knows if that's possible. Even if it is, creating and controlling such a bubble might destabilize spacetime itself. There's also a safety issue. As the bubble moves, it could accumulate radiation and particles at its leading edge. When you stop, they'd release in a catastrophic burst, potentially destroying everything in front of you. The Alcubierre Drive remains a beautiful idea on paper, but its path to reality is unclear. And if it does enable time travel, it may do so in ways we can't predict or control. Stephen Hawking proposed that the universe has a built-in defense mechanism against time travel. He called it the Chronology Protection Conjecture. The idea is simple. Whenever conditions arise that would allow backward time travel, the laws of physics intervene and prevent it. Wink. Wormholes collapse. Closed time-like curves destabilize. Quantum effects create feedback loops that destroy the time machine before it can function. Hawking suggested this might be a fundamental law, protecting causality and preserving the integrity of history. Some calculations support this. When particles try to travel through a time loop, they accumulate and create destructive interference. The energy density spikes. Space-time itself may rupture. But here's the unsettling part. So we don't know if the conjecture is true. It's a hypothesis, not a proven law. And if it's wrong, if nature doesn't have this safeguard, then closed time-like curves might exist in hidden corners of the universe, places where the past, present, and future bleed into each other, where causality breaks down and the rules we take for granted dissolve. The absence of time travelers from the future might mean the conjecture is correct. Or it might mean time travel is possible, but so dangerous or rare that no one has succeeded yet. Or it might mean they're here, and we just don't recognize them. 10 theories of time travel, from the proven to the terrifying. Some let us glimpse the far future. Others suggest the past is reachable, but only at a cost we can barely imagine. If you found this journey through space-time fascinating, subscribe to Cosmic Egg for more deep dives into the universe's strangest mysteries, and watch this video next. Thanks for watching.